Hi everyone, welcome back to Radical Chemistry. On this channel, I will be giving lectures on 11th and 12th chemistry topics. They are going to be very useful for your NEET and JEE mains preparation. If you are new to this channel, please take a moment to subscribe so that you watch all my latest videos. So today we are going to learn resonance. So before getting into the resonance, let's revise the previous topic. We have discussed what is electron displacement. We have also discussed inductive effect in detail. We have discussed about the plus I groups and minus I groups. Plus I groups are electron donating groups and the minus I groups are electron withdrawing groups. We have also discussed how to determine the acidic strength of a carboxylic acid. Minus I groups are increasing the acidic strength of carboxylic acid, and we have also discussed the acidity of alcohols. In this case also, minus I groups are increasing the acidity of alcohols, and the basicity of amines, where plus I groups are increasing the basicity here. And we have also discussed stability of carbocation and carbanion, where carbocation stability is increased by the presence of plus I groups. Okay, when a carbocation is present, where the carbocation is an electron deficient species, it is stabilized by having a positive inductive effect group. More the number of plus I groups, more is the stability of a carbocation. And also the carbanion, the stability of carbanion is increased by the presence of minus I groups. The stability has been increased by the presence of minus I groups, and the presence of positive I groups has decreased the stability of carbanion. So we have learned the entire inductive effect. Next electron displacement effect is the mesomeric effect. So in the previous video I have said that there is a similarity between the mesomeric effect and the resonance. So in NCERT book, both resonance both the resonance and mesomeric effect are given as the same topic, but there is a slight difference. I will be discussing that also. But before getting into the mesomeric effect, you need to understand what is resonance. Without understanding how to write a resonating structure and knowing the stability of a resonating structures, you can't understand the topic mesomeric effect. So in this video I am going to talk about the resonance, and we'll also see the types of molecules which exhibit resonance and also writing the resonating structures in this video. So what is a resonance? To explain this phenomenon, benzene is the best example. I'll number this molecule where 6 carbon atoms are present. 1, 2, 3, 4, 5, 6 carbon atoms are present. You can see double bonds, 3 double bonds which are placed at carbon 1, carbon 3 and carbon 5. Okay, 3 double bonds are present. So in the first video of GOC we have learned that C single bond C has the bond length of 1.54 angstrom, and the C double bond C bond length will be 1.33 angstrom. Yes, now when you are seeing this molecule, we'll assume that the bond length between C1 carbon 1 and carbon 2 will be 1.33 because it has a double bond, and also the bond length between carbon 2 and carbon 3 will be 1.54, which has a single bond. So this is our expectations from this molecule. But the reality is all the bond lengths of benzene are same. All the bond lengths of benzene are same. So how does this happen? And the experimental bond length, the value of an experimental bond length is 1.4 angstrom approximately. So the experimental value came out as 1.4 angstrom, which is between the 1.54 and the 1.33. That is the single bond and the double bond. So by seeing this experimental value, we came into an understanding that the pi electrons in this molecule are not at the same position. They are getting delocalized. They are moving within the molecule. They are moving within the molecule. When we are saying that electrons are moving within the molecule, we can write the molecule like this also. So we can write the bonds at different position also. We can write the bonds at different positions. Now we'll number this one also, number this molecule 1, 2, 3, 4, 5, 6. This is also a benzene molecule, but you can see the position of double bonds has been changed. Here the double bonds are between carbon 2 and 3, 4 and 5, and 6 and 1. So we can write the benzene molecule in both the ways. We can write the benzene molecule in both the ways. And these two structures are called as resonating structures. They are called resonating structures. So by understanding this, we can write the definition of resonance as a phenomenon. It is a phenomenon where the molecule can be represented in two or more ways. Which differ in the electron distribution, but not the atomic arrangement. This is important. So we have to remember only the electrons are moving. Not the atoms. The arrangement of atoms should be same. Okay. Now, as we have discussed, so this is one resonating structure and this is a second resonating structure. The electrons are moving towards the second. Electrons are moving in this way to form the second resonating structure. So to represent the conversion of one resonating structure to the other will be with a double-headed arrow. Double-headed arrow is used to represent the conversion of resonating structure into the other. Okay, so now we have seen the definition of resonance and how the electrons are moving and how to represent the conversion of one resonance structure to the other, and also we have learned that the arrangement of atoms should not change. The arrangement of atoms should be always the same. Okay, now what are the molecules which are undergoing resonance? What is the criteria? The important criteria for resonance is conjugation. A molecule needs conjugation to undergo resonance. The conjugation may be of a pi bond and a pi bond. That means the two pi bonds should be in the alternate position. So there are 5 types where you can see conjugation. One is the pi and a pi bond, where the pi and pi bond should be in the alternate positions, and you can also see pi and a positive charge, pi and a negative charge, and also pi and a radical, and also pi and a lone pair. When you see a molecule with any of this type of conjugation, you can say that the molecule has resonance. That means the electrons are getting transferred within the molecule. This is important. The electrons will not transfer to the other molecule, but only the movement will be only within the molecule. We are going to see all these 5 types of conjugation in this video. We are going to know how the orbitals are placed in these types of conjugation. Okay. Before getting into that, let's study about the resonance hybrid. What is a resonance hybrid? Okay, just now we have learned about the resonating structures. We have learned about the resonating structures and also how to denote the conversion. Okay, but these resonating structures are not real. They are not real. They don't exist. The resonating structures are not real molecules. They are our imaginations. We are imagining that the electrons will be moving in a particular direction. So we are writing the resonating structures. What is the real molecule? Resonance hybrid is the real molecule. And how do we represent it? So we have learned the resonating structures of benzene. So we'll see the resonance hybrid of benzene only, so that we can understand easily. So we have written the resonating structures of benzene. This is one structure and this is the other structure. Okay. Now the electrons have moved, shifted towards the other positions. Now the resonance hybrid would have the regular 6 carbon. So here when you see the resonating structures, only the pi electrons are moving. Okay, only the pi bonds are moving. And the sigma bonds, the skeletal structure is intact. So we are going to write the sigma bonds with a thick line. We have wrote the sigma bonds with a thick line. Now the movement of electrons should be represented with a dotted line. The movement of electrons should be represented with dotted line. And also benzene is a pi-pi type of conjugation. Okay, benzene is a pi-pi type of conjugation. We'll also see how to write the resonance hybrid for other types of conjugation, pi, positive and other remaining three. So we are going to see the orbitals and writing the resonating structures and also the writing hybrid structure. And I would like to mention one more point here, that is the conjugate positions. I will explain it with an example. Suppose we are taking this compound. So you can see three double bonds are in conjugation. Three double bonds are in conjugation. They are placed at the alternate positions. So we have to count how many positions are in conjugation. That is, this is one, and this is second, and this is third, where one double bond is at carbon 1, carbon 2, and carbon 3. So there are three double bonds. So three double bonds are in conjugation now. When three double bonds are in conjugation, now note one point. The number of conjugate positions. The number of conjugated positions will always equal to number of resonating structures. I will denote resonating structures as RS. Okay. The number of conjugated positions is always equal to the number of resonating structures. Okay, we'll see one more example to understand. CH2 double bond CH. So how many positions are in conjugation here in this molecule? You can see a double bond which has a double bond in the alternate position, and you can also see a positive charge here. I have just told pi and a positive charge are also considered as conjugation. So there are three positions which are in conjugation. So three positions, that means they will be having three resonating structures. Okay, you remember this point. The number of conjugated positions will always equal the number of resonating structures. Now we'll see the arrangement of orbitals and also how to write resonating structures and a resonance hybrid in all the five types of conjugations. Okay. So there are five types of conjugation where you can see the delocalization of electrons. First one is the pi-pi conjugation, where the p orbitals are parallel to each other. So you must also understand when the electrons are getting delocalized or moving in a molecule, the electrons must be loosely attached. You cannot delocalize the electrons from a sigma bond. Pi bond is a weaker bond because it is formed by the overlap of p orbitals. Okay. Now all the p orbitals are parallel to each other. So there are chances of delocalization here. So the p orbitals which are in conjugation are parallel to each other. So this pi bond is in conjugation with this pi bonds. When you are writing the resonance hybrid for this, you write it as you write resonance hybrid like this. Coming to the next type of conjugation where pi bond and a positive charge are in conjugation. See, this carbon has a positive charge over it. That means an electron withdrawing group has detached with this molecule, leaving a positive charge on the carbon atom. Now this carbon atom is electron deficient, and this is in conjugation with the pi bond, where the hybridization of this particular carbon will be sp2. So the p orbitals are in pair. The p orbitals are lying parallel to the p orbitals of pi bond. This p orbital of carbocation is lying parallel to the p orbitals of double bond. So the delocalization of electrons occurs through the conjugation. And how to write a resonating structure for this? You have to denote it with a double-headed arrow, and these pi electrons are shifting towards this thing. So this carbon deficient species, carbocation, needs only one electron to be stable. So from these two electrons, out of two electrons, only one electron is shifted towards this bond. So forming a double bond here. Okay. Now the new double bond is formed here, and the other electron, that is the remaining electron, is stayed with this carbon, and it gains a positive charge. So this is one resonating structure, and this is the second resonating structure. And when you are writing the resonance hybrid, you denote it as with a dotted lines, and on the carbon 1 and the carbon 3 positions, it is gaining a positive charge. So you denote with a delta positive, that is in the resonance hybrid, you denote with the partial positive character, and the C2 position is getting the partial negative character. So what do you understand when suppose this molecule is given as a substrate in the exam, and the reagent is a nucleophile, and when they are asking you to react with this particular substrate molecule, you assume that the nucleophile is going to attack this particular position. But that is not the case in all reactions, because this molecule is in resonance. There is a delocalization of electrons here, where you can see this is the resonance hybrid, this is the real molecule, where both the C1 and the C3 positions are gaining the positive charge. So nucleophile may attack C1, or it may attack the C3 position as well. So you have to understand, if the molecule, if the substrate is given, you need to think for a moment whether it is having a resonance, whether there is a chance that whether the nucleophile is attacking the other position. So you have to think about it as well in the exam, because they are going to confuse you with the options. As you can see, this molecule is symmetrical, whether carbon 1 and carbon 3 are chemically equivalent because they are having the same atomic arrangement. Now there won't be much difference if the nucleophile is attacking C1 or C3, that doesn't matter. But if there is a substitution at any of the carbon, and if the carbon chain is different, then the product is going to be the different. And we are going to discuss it further when we write the resonating structures for many other examples. Once we are done with the type of conjugations, we'll start writing resonating structures. Okay. And the third type of conjugation would be negative and pi. So here negative charge in conjugation with the pi bond. So here the movement of electrons will be different. Here the carbon is electron deficient, so it is gaining the electrons from the pi bond. Now here the negative charge is electron rich. It will give away the electrons towards this bond, and these electrons, the pi bond electrons, are taken towards this carbon. We'll write the resonating structure, second resonating structure here. Now this has gained the new pi bond, and this carbon will gain a negative charge over it. So you have seen there are two conjugate positions. Yes. So the number of resonating structures would be same, 2. This is the one resonating structure. This is the second resonating structure. And the resonance hybrid would be propyl group with a dotted line where the delocalization has been happening. Now, what are the carbons which are gaining the negative charge in resonance structures? C1 and C3. So, we'll write delta negative and delta negative over C1 and C3, showing that these two have an electron negativity nature. When an electrophile attacks, it will be attacking C1 and C3 but not the C2 position. C2 position will have the delta positive charge. Okay, this is about the negative charge and a pi bond. And then comes to the odd electron, where the odd electron is a radical, free radical. Odd electron and a pi bond are in conjugation. So radical species are also electron deficient. They are formed due to the homolytic division. So the one electron is taken away and the other electron is remained with this molecule. Now, so the movement of electrons will be towards this bond, but there is a radical here. So the breakage of bond would also be homolytic. Only the one electron is shifting towards this, and the other electron goes to this carbon. I have told you while discussing the bond cleavage, you have to denote homolytic fission with a half-hooded arrow. Okay. Now this carbon is forming a radical here, and the new pi bond is formed between these two carbon atoms. Okay. Now the resonance hybrid would be the dotted lines. The delocalization is represented with the dotted lines, and I have told you this is the electron deficient species. So delta positive and a delta positive over C1 and C3 positions, and C2 gets a delta negative character. Okay. Then coming to the lone pair and the pi type of conjugation, where any atom containing a lone pair is in conjugation with the double bond, that means the pi bond, will have a resonance. This will have resonance. Now this lone pair is in conjugation with the pi bond. Okay. We'll write the resonating structure here. So the lone pair of electrons would be moved towards this bond, and these pi electrons will be moved towards this towards the carbon atom. So you will get the structure as NH2 positive, because the nitrogen has formed a new pi bond. So nitrogen is forming 4 bonds, so it gains the positive charge over it. It gains the positive charge over it, and this carbon gains a negative charge over it by accepting the electrons. So this is one resonating structure, and this is the second resonating structure. So the real molecule, the resonance hybrid, would be something like this: NH2 with the delocalization of electrons denoted by a dotted line, and we will be writing delta positive, delta negative character on this molecule, on this hybrid. So in this molecule, nitrogen is gaining the positive charge. So we'll write delta positive, and carbon is gaining a delta negative charge. Okay. When an electrophile is attacking, it would attack on the carbon atom, and if the nucleophile is attacking, it will attack on the NH2. Okay. Now this is about the types of conjugation. So we have discussed the arrangement of orbitals in pi and positive charge pi bond types of conjugation. We'll also see these 3 types. Okay. Now p orbitals are, these 2 p orbitals are in parallel to each other, and the negative charge and the electrons in the negative charge will be held towards downside. So these electrons are now parallel to each other, so there will be delocalization. And coming to this particular type, where free radical is in conjugation with the pi bond. Now free radical is a sp2 hybridized carbon, so the p orbitals are in parallel with each other. And coming to this lone pair, the lone pair are in conjugation with the p orbitals. Electrons in the p orbitals are in conjugation with the lone pair, so there would be delocalization, and you can observe the resonance. So these are the types and the arrangement of orbitals and writing the resonance hybrids. Okay, we will be discussing how to write a resonating structure for variety of molecules in our next video. So these are the types of conjugation. Now we'll see what are the conditions for a molecule to undergo resonance. So the condition for resonating structures would be the arrangement of atoms should not change. I have told you in the beginning of the video that the arrangement of atoms should not change. Coming to this molecule, you can see a pi bond and the lone pair are in conjugation with each other. Okay. Now these pi electrons are moving towards the oxygen, as oxygen has an electron withdrawing nature. So these lone pairs are shifted towards this bond. So the resonating structure would be something like this. Oxygen has gained the negative charge, and this oxygen has gained the positive charge, because it has formed 3 bonds. It has formed 3 bonds. It has formed 3 bonds. Now these 2 are the resonating structures, and we'll see one more molecule. Okay. Now here also the pi bond electrons are shifting towards the oxygen atom. Oxygen is gaining the negative charge, and carbon will gain the positive charge. So when the carbon is gaining the positive charge, this carbon is giving away 1 proton. This carbon is giving away 1 proton, gaining a negative charge. Now this positive and negative charge will come together and form a bond, pi bond. So this carbon has detached 1 proton, H plus. So that would go and join the oxygen atom, which has a negative charge. So here you can observe the arrangement of atoms has changed. The hydrogen atom from here, it is moving towards the oxygen atom. So now this is a tautomerism. Okay, this is tautomerism, and this is resonance. So this is the only difference you can see between the tautomerism and a resonance. And coming to the other point where the number of paired and unpaired electrons should be same in all the resonating structures. Number of paired and unpaired electrons should be same. We'll see this example only where you can see in this resonating structure there is one pi bond. In this structure also there is a one pi bond. Okay. Now this oxygen has two pairs of lone pair, and this oxygen is also having two pairs of lone pair. And coming here, this oxygen is having one pair of lone pair. This oxygen is having one lone pair, and this oxygen is having two lone pairs. So here you have 4 lone pair of electrons, that means 8 unpaired electrons. And coming here you have 3 lone pair, that means 6 unpaired electrons, and counting the negative charge has 2 electrons. So total number of unpaired electrons are 8. So the total number of unpaired electrons in this resonating structure, in the first resonating structure and in the second resonating structure are same. By practicing more and more questions, you can understand this point, and we'll also see one more example here. Nitro. This is one resonating structure and resonating structure. You can see oxygen has 2 lone pairs. Here also oxygen has 2 lone pairs. Nitrogen has 1 lone pair. Here also oxygen, 2 pairs on oxygen and 1 pair on nitrogen. So the unpaired electrons are 1, 2, 3, 4, 5, 6. 6 pairs of unpaired. 12 electrons are there which are not paired, which have not formed bonds. And coming to this molecule, 1, 2, 3, 4, 5, 6. So 6 pairs. That means 12 electrons. So the number of unpaired electrons are same in both the resonating structures. And coming to the number of bonds, 1, 2 and 3. 1, 2 and 3. So each has formed same number of bonds. Each has formed, this has formed one pi bond, and this molecule has also, this structure has also formed one pi bond. So the number of pi and sigma bonds are also same. And the other rule which I want to mention it here is the resonating structure. The resonating structure should follow octet rule. Okay. Whenever you are writing a resonating structure, you should see whether the entire molecule is obeying the octet rule, whether the maximum number of bonds, whether the structure is forming the maximum number of bonds, and the charges on it are appropriate or not. We have to understand this. You can understand this more deeply while practicing questions. For now, I will give an example for this point. Okay, we have taken a benzene molecule which is substituted with a ammonia. Now, nitrogen has formed 3 sigma bonds with 3 hydrogen atoms and 1 with the benzene molecule. So it will gain a positive charge on it because it has formed the maximum number of bonds. When you are writing a resonating structure for this, these 3 pi bonds are in conjugation and also the positive charge is in conjugation. You should know how the electrons are moving. Okay. For suppose, we are moving the electrons towards this bond from nitrogen. That means electron is forming pi bond here, and you are shifting these electrons towards the next bond. Then the structure would become something like this. But does this molecule follow octet rule? No, because the nitrogen has formed 5 bonds here. Nitrogen can never form 5 bonds. The maximum number it can form is the 4, that is with a positive charge. It can donate the 3 electrons in the p orbital to form 3 sigma bonds, and by donating the lone pair of electrons, it will gain a positive charge. Other than that, it cannot form a single bond. So, writing a resonating structure where you show that nitrogen is forming 5 bonds, that is a blender miss. You have to follow the octet rule. Okay, this is the very important point. Okay, very important thing. You should remember this comes the first rule when you are writing the resonating structure. This comes the first. When you are writing a resonating structure, you have to follow the octet rule first. Okay, so these are the conditions when you are writing a resonating structure. You have to remember this point. So till now we have learned what is the resonance, and we have also learned how to denote a resonance hybrid, and also the types of conjugation, and we have also learned the conditions for writing resonating structures. So in the next video I will be showing you how to write resonating structure, and we'll also discuss their stability. Okay, so the concept of resonance would be clear in your mind. So if you have any doubt regarding this particular concept, particular video, you can comment down below. I would be glad to clarify all your doubts. If you found this video helpful for you, then please like this video and also share it with your friend. Subscribe to Radical Chemistry to watch the latest lectures that I upload. Thanks for watching.